In Part 5 of the Unit 5 notes, we will be covering ionization energy, electronegativity, and electron affinity. Ionization energy, with the unit of kilojoules per mole, is the energy required to remove an electron from an atom. The outermost valence electrons will have lower ionization energies than the inner shell electrons. Think of ionization energy as an indication of how strongly a nucleus holds onto its valence electrons. With this table on the bottom left, we will be comparing the ionization energies for some of our elements towards the top of the periodic table. First up, we have hydrogen. Hydrogen only has one valence electron, or one total electron, so the ionization energy will be fairly high. It gets even higher for helium because this is a noble gas, and we know that noble gases do not like to give up electrons. But when we get down to lithium, we can say that there is a significant drop in the amount of ionization energy, so only 520. And that is because this last electron, lithium would like to get rid of. It would like to remove this electron in order to become more stable like a noble gas, in order to have a configuration of 1s2. So it's not going to resist if an atom is trying to take its electron away. So this number is going to be pretty small. But once that electron is taken away, it's going to really hold on to the last two electrons that it has left. So we can see that the ionization energy will increase significantly. Now if I go down to beryllium with a configuration of 1s2, 2s2, there are two electrons that beryllium would like to lose. So the ionization energy for the first two electrons is going to be significantly lower than once you try to take off that third electron, where there is a huge jump. We're going to see something similar in boron. Boron has 3 total electrons that it would be willing to give up in order to be like a noble gas. So we have 800, about 2400, 3600, and then it jumps up to 25,000. So once we get rid of those first 3 valence electrons that the atom doesn't really want to hold on to that well, then your inner core electrons are going to have a much higher ionization energy. In general, as we go down our list here, we can see that it is going to increase significantly as we get towards our nonmetals. We know that nonmetals are more likely to want to gain electrons to become like a noble gas, as opposed to a metal, which is likely to want to give up electrons. A contributing factor in the amount of ionization energy which is required is electron shielding. As more shells of electrons are added, the electrons furthest from the nucleus become shielded from the positive charge by the inner shell electrons. This is called electron shielding, and it makes it easier to remove the outer electrons. So what this is essentially saying is that the more shells of electrons you have, the easier it is going to be to pull off that last electron. And you can see what we're talking about here with this diagram. In the center, we have our positively charged nucleus, and on the outermost shell, we have our electron of interest. The more negative charges there are standing in the way between the nucleus and the electron that would be removed, the less likely that this electron is able to feel the full positive charge of the nucleus. It basically has all these negative blockers in between. So the more shells you have, the greater degree of electron shielding there is, which is going to make it easier to remove that electron. Ionization energy trends. As you move from left to right across a period, the ionization energy is going to increase. This occurs as we move towards the noble gases. The atoms are going to be more condensed. The negative electrons are going to be closer to the proton, so they're going to be more attracted. We also are going to be moving towards the nonmetals, which would prefer to gain electrons as opposed to losing them. As you move down a group, the ionization energy is going to decrease. So that would be like going from helium to neon to argon to krypton and so on. So these are all noble gases. They all still do want to resist having that electron removed, but it will get significantly easier the bigger the atom gets. And that has to do with the electron shielding we were discussing on the previous slide. The more shells of electrons that are in the middle blocking that positive and outermost negative charge from each other, the easier it will be to remove that last electron. Why does ionization energy increase when moving from left to right across a period. This has to do with the level of attraction. We know from our atomic radius that as we go from left to right across a period, the atom is actually getting smaller. Since it's getting smaller, the protons and electrons are going to be closer together. That means that there is increased attraction, which makes it more difficult to remove an electron. Electron shielding would not be a factor here, because as we are going from left to right, we have the same number of shells in total. For number 2, why does ionization energy decrease when moving down a group? This has to do with the electrons being further from the nucleus. And for that, I actually want to clarify, we're talking about the valence electrons. So the valence electrons, the ones furthest from the center of the atoms, the ones that we would be removing, they are further from the nucleus, which means less attraction. We also know that as we go down a group, we are adding more and more shells, which should increase the amount of electron shielding. Since there is more electron shielding, it would also be easier to remove an electron from the last shell. Or we could say there is less ionization energy because of that. There is a pattern in group 3 elements of having a lower ionization energy than those in group 2. We can see an example of that right here on this graph. It's very slight, but it is slightly easier to remove an electron from, say, boron as opposed to beryllium. Why does this occur? In order to answer this, you should consider the electron configurations. So if we were to look at one for beryllium, it would be 1s2 and then 2s2. Whereas boron is 1s2, 2s2, 2p1. While both of these have electrons within the second principal quantum number, the second energy level, we know that the p shape is slightly higher in energy. It would be slightly more favorable to lose one electron from this 2p orbital and have a stable 2s subshell underneath, as opposed to removing an electron from an already somewhat stable 2s subshell. So the fact that you have this p electron here that's kind of hanging out by itself, it makes it a little bit easier to remove that electron. Another way of saying that is that it is easier to remove this unpaired p electron as opposed to the stable or slightly more stable and paired s electron. The electronegativity of an element indicates the relative ability of its atoms to attract electrons in a chemical bond. Electronegativity values are expressed in terms of a numerical value of 3.98 or less. The units are called Paulings, named after American scientist Linus Pauling. The trends for electronegativity is that as you move from left to right across a period, the electronegativity increases. So there is a stronger desire for electrons as we move towards the right. As you move down a group, the electronegativity decreases. So as we're going down a family, atoms are less able to hold on to those electrons. Here we can see the electronegativity in another way for the entire periodic table. So this is color-coded. Low levels of electronegativity are shown in a darker green, and then higher levels are shown in a red or an orange. So we can see that our nonmetals are going to have higher levels of electronegativity as opposed to our metals. Why would elements on the right side of the periodic table, such as the halogens, have a higher electronegativity as opposed to elements on the left side of the periodic table, such as the alkali metals? Well, if we think about the elements on the left side of the periodic table, they all have one valence electron, and these elements have 7 valence electrons because they're in group 17 or 7a. Now, if I have one valence electron, it's significantly easier to lose that one electron than it is to gain 7 electrons to become like a noble gas, to have that noble gas configuration. Whereas on the other side, it is easier to gain 1 electron as opposed to losing all 7. So since these are metals which would prefer to lose 1 electron, they're going to have a low electronegativity because they don't really want more electrons. They're trying to lose the electron they already have. So these metals would prefer to lose electrons. Whereas these elements over here, these nonmetals, they would prefer to gain electrons. So since they want to gain electrons, they're going to have a high desire for electrons within a bond. So they're going to have a higher electronegativity. Electron affinity is defined as the change in energy, in kilojoules per mole, of a neutral gaseous atom when an electron is added in the form of a negative ion. In other words, it is the neutral atom's likelihood of gaining an electron. The trend is essentially the same as what we saw for electronegativity. As you go from left to right, the electron affinity is going to increase. And as you go down a group, it's going to decrease. So the highest electron affinity and the highest electronegativity is going to be towards the top right-hand corner. That concludes Unit 5 Notes Video Part 5. When we come back for Part 6, we'll be looking at metallic character as a trend and the periodic trend summary as a whole.